Hey everybody, here we are in Unit 10 still, symmetry and transformations. So last in 10.1 we did symmetry, today we're doing transformations. We're looking at these types of transformations, basically because they're called translations, reflections, rotations, and dilations. And you've probably done these in a previous class. So let's get started. All right, so a transformation, very formal definition. Translation is a transformation that maps all the points of a figure in the same distance and in the same direction. So hopefully that will make more sense as we move along and look at some examples. So here's kind of a visualization of this idea of a translation. Basically, it's a slide. So if you look at the bottom triangle, the one I'm calling pre-image, the pre-image means that that's the original shape. The image is its copy. So if you look at the pre-image has been slid diagonally up to the image's spot. You can tell that by the way its arrow is pointing in the direction that it was slid. Okay, so this arrow is known as a translation vector, and we'll look at it in this sense when we do the notation. Instead of having soft parentheses, these are what I call soft parentheses, like a point would have. We're going to put these kind of caret things on it, but it's going to kind of look like a point. It's going to be a number, comma, a number, but that's going to have, those carets are what's going to tell you we're talking this thing's a vector. That vector tells you, the reader, which direction this thing headed off in. You have the pre-image, you apply a vector, and it's moved to the left and the right and up and down, and that's what those two numbers will give you. Let's take a look at this figure over here. Let's assume this is my pre-image, okay? And all right, sorry about that. I got interrupted by the announcements going on. But anyway, I have over here on the left-hand side is a pre-image. And over here on the right-hand side are three choices that represent what could be a translation. Two of them are not translations. There are some other type of transformations. So let's take a look and see if you can identify which one they are. Come back and check your answer. All right, so hopefully you picked one. What I know is this, it can't be B because if you look at the B, the right-hand side has that long side of the arrow, and that's on the left-hand side over there. So it didn't simply get slid over there. It got probably reflected over there if you look at it, kind of flipped, right? Okay, so then this one's completely upside down. That one can't be it, so of course we left with A. What I can see is A was slid up to that position. What we'll find out is that that slide is really a left and right slide and then an up and down slide. Okay, so it went, in this case, it went over to the right and up, and we'll have to identify how far. Now we can look at translations in the coordinate plane. Okay, so let's take a look at this figure. We have the blue figure is my pre-image, and the green one is my image, my copy. Okay, so what we find out is that, just as we had hoped, that first number tells the x direction how it's moved, and the second one tells us the y direction. Okay, that's a good thing. That's just like in a regular point. A point, the first coordinate is an x, is related to the x, and the second one's y. So if we take a look at this thing, the vector, and it has those caret things on the either end, kind of hard brackets, tells us to move a point. Let's start with this point right here. It tells us to move a point in the positive x direction of 6, and then down, that's negative 3. And there it is. That's the point. So if this was point A, hopefully you'd realize this is point A prime. Okay? All right, whenever we have a pre-image, it's going to have letters on it and everything. When we write the image, the copy, we always label it. This is going to be true on your homework. So if this is B over here, this becomes B prime. So always make sure that you're labeling your homework images, the copies, with the correct notation. Okay, put me on pause and see if you can identify what vector would I have to use to move point A to the red dot. Okay, so go ahead and put me on pause and come back and check your answer. Remember to use the correct notation, those brackets. Okay, for me, I got -5, 4. So basically, that says I went to the left 5, 1, 2, 3, 4, 5, and then I went down 4. 1, 2, 3, 4. And that is true. So let's go ahead and see if you can now tell me what would be the name of the red point. Hopefully you would say A prime because it's its copy. Let's move. Now another transformation we want to look at is reflections. Reflections across a line R, called the line of reflection, is a transformation with these two properties. First, if a point A lies on the line, then its image, A prime, is that same point. That makes sense. It's going to reflect right onto itself. The other property is this. If B is represented here and B is its reflection point over here, let me start over. If B is over here in the pre-image side, right? And it doesn't matter if we're reflecting left or right. I just tend to, when I'm setting them up, it starts on the left and reflects to the right. But if B represents some point on the pre-image, B prime is its reflection, right? And what we find is that the reflection of that is going to point to a point in such a way that when I connect B with B prime, it creates a perpendicular to the line of reflection, and those two sides, the left side and right side of the reflection, is the same. In other words, if a point is so much distance away, let's say it's 3, its reflection is 3 on the other side as well. Okay? So there you have it. There's the reflection of that arrow, if you will. And again, this point is the same on both sides. Okay? So you can create this image if you're given it on a piece of paper. You can take your paper and just fold it along the line of reflection, and you'll see the original pre-image through the paper, and you can just trace it to get the image. So let's take a look at reflecting a segment, in this case, across a line. You know, let's take a look at reflecting it across the line of this one right here. This is the x-axis. We know this to be y equals 0. That's the equation for that line. Y is 0. Now, to get its reflection, all we have to do is, this is super easy. You're going to love how easy this is. All you got to do is walk straight to the line. I just walked up to the green line. I counted that it was 2, and I walked straight away from the line. There's the other point. So there's B prime up there. Here comes A. I counted 3. And 3 above, there's A prime. Okay, connect them, and there's my reflection. Let's look at a couple other. I'm just going to rattle through these pretty quickly. I'm going to put it on pause and ask you to think them through. I would draw them and think them through on your own. Here we go. Okay, so there's our horizontal or vertical line. This would be x equals 0. Okay, let's go ahead and see if you can reflect AB across that line. Okay, that's easy enough. Now let's take a look at the points, the coordinates, okay? This A over to the right and this B over to the right. Now if you take a look at this, when we reflect across the y-axis, the red coordinates, 1, negative 3, becomes negative 1, negative 3. In other words, what I really want to point out is when we reflect across the y-axis, the x changes sign. Okay? So the rule for this is this. If I have some point, let's say, I have some point xy, it maps to a point opposite of whatever x is. If it's negative, it becomes positive. If it's positive, it becomes negative. But the y stays the same. Okay, so that's kind of what we call a reflection rule, right? It takes y or x and y and moves it to whatever the x is, the opposite, and then the y. Let's see if you can do the same thing. Let's go back to the previous problem and see if you can come up with the rule for this one, where you're reflecting across the x-axis. I hope that you got this. The x stays the same in this case, but the y changes sign. So if it was positive, it became negative. Okay, and if it's negative, it became positive. All right, very good. All right, let's go back and look at the translations. In the translations, let's suppose you're given a vector, right? and the vector says AB. In the case that we were given, it was 6, -3. Now, it's not about the sign. It's just A and B represent some numbers. If you're given that vector, then it maps the points, whatever it is in your pre-image, the X and Y coordinates, and it just simply adds the A and B to the previous coordinates to get the new coordinates. And so, again, if A is negative, then you would actually end up subtracting A. And if B was negative, then you would subtract B. But this is basically the rule that you want to know for translations. Probably the easiest way is just remember if it's on the graph, count. All right, the green line in this one is y equals x. You're going to have to memorize this one. Now, this is nothing new. This is from Algebra 1. Y equals x is the line that's created by starting putting a point at 0, 0. If I plug 0 in for x, I get 0 for y. And then going over 1, up 1, over 1, up 1, and it continues to go that way. So if I give you, hey, reflect this across y equals x, you're going to have to create your own y equals x problem. So here's the rule that I want you to remember for reflecting across the y equals x. Then we'll talk about doing it on paper. So you take your x and y and you flip it and then negate it. It's kind of like taking the contrapositive of a conditional statement if you think about it. You flip them and then negate it. Okay, so if x is negative, it becomes positive. If it's negative, it becomes positive. If it's positive, it becomes negative. Oops, I'm sorry, I totally said that backwards. You just simply flip it for y equals x. So if the point is 5, 4, it becomes the point 4, 5 when you reflect it across the y equals x coordinate plane. So what I would like you to do is take that A and B, find its coordinates, and then reflect it across the y equals x. Plot those new points, come back and check your work. All right, hopefully you have, first of all, labeled your reflection correctly with A prime and B prime. If you haven't, you need to go back and change that, okay? Here's what I know from symmetry. If I take this picture and folded it along this y equals x, whatever my pre-image, this side that's over on this side, should map to the other one on the other side, okay? So if you're not sure what's going on, go back and look at that part of the video again and make sure you understand that. So here's the rules that I need you to know, okay? Now you have a formula sheet, you can throw them on there if you want, but basically it's these rules. Make sure that you understand them and how to work with them, okay? If you're having trouble with them, then you come back and see me. Make sure when we're in class, we're practicing it and you understand it. All right, let's take a real quick look at rotation. A rotation of an object is about a point R, or P or Q or O, it doesn't matter. In this case, we're going to talk R, called the center of rotation. It's a transformation where every point of the object rotates about R, some degrees of X. So suppose I have this arrow like this thing, and I want to rotate it so many degrees, okay? So what I would do is I need to figure out kind of where it's going to be. Now, helping you just understand what rotation looks like is this picture, okay? So what I'm going to do is I'm bringing my protractor, and I'm going to rotate it around so that it goes right up through that image. There we go. Whoops. It's this one. And so I have this on, I have the that on R, and then I made sure that the zero, see those zeros for this side, the zero lined up with the arrow's pointy part, okay? So suppose I had a rotation of some arrow, I'm sorry. So here's a blue arrow, that's my pre-image, the red is my image. And so I could pull out my protractor and figure out how many degrees of rotation is that, okay? So I'm gonna grab this thing and I'm gonna run it out. And so remember, we're on the inside. We started with 0 degrees. The outside numbers are for if you're coming the other way. So it's about 80 degrees, okay? So if you take a look at this thing, or 60 degrees, I'm sorry. So if you look at this thing, it rotated about 61 degrees. Yeah, probably more like 60. I measured it a little bit over. Okay, so that's basically what an image looks like when it's been rotated. Notice that it looks completely different than, say, a translation. A translation, remember, is when they take it and you slide it around. It keeps the same position. this goes into a different place, right? Or orientation. It keeps the same orientation. It's pointing in the same direction. You can tell a rotation by the fact that it's pointing in a different direction. So let's look at the rules for rotation. Positive rotation is counterclockwise. This is positive rotation. And negative rotation is clockwise, completely opposite of what you would expect, I think. But let's make sure you understand why. If you understand why it's this way, it might make more sense. We're in the world of math, and so it comes from that world, not from the world of clock. So if you remember, coordinates are the coordinate plane has quadrants, and this is quadrant 1. Quadrant 2 is not down here. It's actually to the left. That's quadrant 2, 3, and 4. Okay, and so it would make sense then. Rotation is this way, would be a positive direction. You know, kind of going from quadrant 1, 2, 3, 4, 1, 2, 3, 4 is counterclockwise. So remember, counterclockwise is negative, positive is, I'm sorry, I said that backwards, don't remember that. Counterclockwise is positive and clockwise is negative. So if I tell you to rotate something 60 degrees, since there's no sign out in front of it, we'll assume it's, oh my goodness, we're going to assume that it's counterclockwise. If I tell you to rotate something negative 60 degrees, then you're going to rotate it in the clockwise direction. I got myself all goofed up on that. Let's move on. Okay, so here's my rule for rotation. It's really easy when we're in the quadrant plane. You take your x and y value and you flip and force it. Now listen closely. You got to really pay attention to this. If I have a point, say this A, which has the coordinate 2, 1, and I rotate it 90 degrees, I first of all have to recognize that's a positive 90 degrees, which means it's counterclockwise. Now in the coordinate plane, we're only rotating it 90 degrees every time, or it might be 180 or some factor of 90 degrees. So what I'm going to do is I'm going to realize if I'm in quadrant 1 and I'm rotating point A 90 degrees, 90 degrees gets me over into quadrant 2. 180 would get me down here to quadrant 3, and 270 would get me down here to 240. Okay, and I'll take a look at that with a big round protractor so you can understand that in a little bit better terms. But A is going to map to quadrant 2. Now listen closely. I'm going to use this thing called flip and force. What you're going to first do is you're going to take whatever your x and y is and you're going to flip it. Okay, so whatever the x was now becomes y, and you're going to flip it. That's the first step. Then you force it. So the signs match that quadrant. Let me show you what I mean. So if I've done this right, my pre-image point is 2, 1. I'm going to move it into quadrant 2 by flipping and forcing it. So A prime is going to move to the location of 1, 2, right? But if you think about it, the signs of a point in quadrant 2 do not have a positive and a positive x and a positive y. It has a negative y value or negative x value. So I have to force the x to fit in that quadrant. So it can't be positive 1. It has to be negative 1. Now I'm going to bring in my protractor. Now you don't need to use a protractor. You just need to remember this force and flip, or flip and force. We'll do a couple of these so you make sure you understand it. So there, I've lined up my protractor. If you take a look, sure enough, that's 90 degrees on my protractor. Flip and force. Let's do another one just to see if you can check yourself and understand what it is. Okay, so there's the point, -3, -2. Let's rotate it 270 degrees. So what ends up happening is you flip it every 90 degrees, get into the quadrant you need to, and then force the signs to fit that quadrant. So if in that quadrant the x and the y are positive, then you make sure that they're both positive. But each time you go from one quadrant to another, every time you go 90 degrees, and you're going to do it 3 times here, you flip it. So you go -3, 2, and you just kind of keep on going. So put me on pause, see if you can figure this out, and come back and check your answer. All right, so there's my flipping, okay? Now you don't have to write this down. You might be just really good. Now notice I didn't care about the signs. I didn't keep the negatives or anything like that. I just looked at the numbers. I started with 3 2s. The first flip becomes 2 3, then 3 2, and then 2 3. That 2 3 now needs to be forced. Now I need to figure out which quadrant I'm in. There's the first 90, the second 90, and the third 90. So I'm actually going to need to make sure I force the coordinates to be in quadrant number 2. So I'll go back and see that negatives, or the x's are negative and the y's are positive. I'll just put a negative in there. So the point -3, -2, rotated 270 degrees is the point -2, 3. All right, so here we do dilations. Dilation's super quick. Dilation's basically taking an image and making it twice as big, 3 times as big. That's the scale factor that we're going to do. We call it the K factor. So suppose I have this point C down here, and I have an image to this triangle, and it's 5 units away from it. If I take and draw another triangle that's 5 units further than that triangle, in other words, it's 10 units away from C, twice as far from C, guess what ends up happening? You end up with, I can take and create a figure that's going to be twice as big, right? So if that's 5 and this is 7, let's say, and this is another 7, this is a total of 14. Let's say this one's 9, that means that's another 9. There's a total of 18. And so I can create a figure that's twice as big by now connecting those points. And there you have it, a triangle that's twice as big. Okay, so that's called a dilation. You're kind of pushing out. Now we could do a reduction, and that basically I would take it and bring it in closer to C, and it makes it smaller. Okay, let's see how we do that in the coordinate plane. Okay, so I'm going to take this triangle ABC, and I'm going to make it 3 times as big. 3 times as big. Now doing the coordinate, but I'm not going to draw this thing. I'm just going to simply apply that K factor to the coordinates. It's super easy. What you're going to do is you're going to apply the K factor to the X and Y. You're just going to basically multiply them. Super easy. Let's go ahead and do. All right, there you have it. I just simply multiplied. So if I went and plotted those coordinates, I would find a triangle that is 3 times larger than the original triangle. If I wanted to make it half as big, then I would take it and make my K factor 1/2. Or if I wanted to make it a third, then I would make my K factor 1/3, and I'd simply multiply my coordinates by that number. Okay, wow, that was probably one of the longest videos that we've done, and you've made it. I'm very proud of you. All right, so here's your 5 problems. There's no review problems. These are all from the video, so you have to go back and make sure you understand the video as we go along, okay? Bring these in next class, get full credit. I'm going to scroll through them so those people who have smaller devices, smaller screens can see what it looks like. All right, have a fantastic night.